Welcome back. It's my pleasure to introduce our next speaker, Professor Davide, professor who leads the Adaptive Computing Lab at the National University of Singapore and is the director of Smart Systems Institute. His research interests include robotics, AI, and computational structural biology. In recent years, Professor Hu has been working on robot planning and learning under uncertainty and human-robot collaboration. Now I leave the floor to Professor Hu. We look forward to hear your talk on closing the planning learning loop, autonomous driving, and object manipulation.
Thank you. Yeah, I plan to mostly talk about decision making in the context of sim to real transfer. It's a general idea, and I'm going to give some examples in robot navigation, deformable object manipulation. Sim to real becomes very popular and gain a lot of attention in recent years because of robot learning in simulation. But the first question I want to put out to you is sim to real new? Right? My answer will be, I'm sure a lot of you would agree, no, not really. And for as long as they're robots and their computer simulation, this issue is there. Right? But we used to treat it a little bit differently. Right? We always wanted robots to operate in diverse environments reliably. But we don't know enough about our world, so we make simplifying assumptions and capture these assumptions in a simplified model. And a simulator is just a particular kind of executable model, right? And so now the sim and the real share a bunch of things: the states and actions and objectives, and these designed entities chosen by the robot engineers, but they also may usually differ in robot perception and dynamics. These are the consequences of nature that we cannot actually choose, right? So we take our model and compute or learn a policy and parameterize by some parameters, data, and we take that policy and execute in the real world. And in the old days, we just pray and hopefully that it actually works. And unfortunately, it doesn't. If it doesn't, what do we do? The robot engineer will step in again, and he or she will actually tune these parameters. It could be like the camera calibration parameters and the friction parameters for grasping, or whatever the parameters want to tune. You tune it until it works, right? So now, what I would like to propose to close the sim to real gap is simply to automate the process and remove the human engineer from this loop. Now, in order to do that, I want to make 3 observations. The first one is I kind of already mentioned. A simulator is a model of the physical world. It encodes our assumptions about the geometry, kinematics, physics, dynamics, and perception, and so on and so forth. Right? All models are wrong. Some are more useful than others. Right? And now, if we actually know that we actually have to transfer the policy from the sim to the real, one thing good to keep in mind is don't try too hard. Don't over-optimize the policy in the simulator, and don't overfit. Right? And finally, it'll be really nice if we can make the whole thing differentiable, and that will make it easy to update the parameters and very efficient. This is our main idea, right? So for learning systems, usually we will have to parameterize a policy, for example, using a neural network, which is popular these days. We are going to train this policy using real world data. Now, if we replace the real world by a simulator, then that will create the sim to real gap because of the imperfections in the simulator. Now, instead of treating the simulator as an imperfect surrogate of the reality, what I would like to do is to put the simulator into the policy and treat the simulator as a model of reality. And therefore, thus the policy representation will explicitly encode all our assumptions made about the reality. And then we are going to train it using real world data. Right? So this is what I would like to propose to do. And to implement this idea, we are going to use the differentiable algorithm network, which we came up with a couple of years back. which has two kind of parts in our idea. One is to neuralize the robot algorithm. So what does that mean? That means that we are going to treat the neural network as a computational graph. So every neuron just does some simple computation, and it's like a little programming language. We are going to use this programming language to program our robot algorithm. It could be a state estimator, planner, controller, or whatever that we want to do. And then this neural network will encode both the model of the world as well as the robot algorithm that does the computation. Okay. So, and here's an example of that for state estimation. Just a very simple example, discrete Bayesian histogram filter, which is written over there. Now, if you look at this, so the model parameters are the state transition model and the observation models, right? And the Bayesian histogram filter is just a bunch of linear operations, basically matrix multiplications multiplied together, right? So that B over there is just a vector that encodes the probability distribution over the state space. Now, we know that matrix operations can be encoded as a convolution layer in the neural network, right? That's how we just encoded the Bayesian histogram filter into it. Now, just to give you one more example, the QMDP algorithm, that is just a decision algorithm for planning under uncertainty. And the details doesn't matter. It's a kind of value iteration. We are familiar with the Bellman's equation, right? So again, that's a bunch of linear operations. But because it's decision making, therefore, at some point, we have to choose what is the best action among all the options, right? So we can need a max operator, but that doesn't cause too much difficulty. We can have a max pool layer in one neural network. Finally, value iteration is an iterative algorithm. Therefore, for each iteration, we need a convolution layer for the linear operation and a max pool layer for the maximum operation. And we have to repeat this k times for each of the iterations. Right? So that's how we encode the robot algorithm into the neural network. Now, the second part of our idea is that now we can encode various different sorts of algorithms into the into a network. We can have a state estimator, can have a planner, we have a controller. We can connect all of them together into a complex system by simply putting the output of one module into the input into the next module, right? And we can train this entire system end to end. Now, in the last few years, we have already got all sorts of different modules for state estimation and fully observable decision making, partially observable decision making, control, and so on and so forth. We have a lot of available modules right now, right? Now, go back to my little example that I'm going to put them together. So I mentioned we have a state estimator and we have a decision maker, and we will connect them together. So this is our representation of learning system. It's just a policy, right? This is policy is parameterized by the model parameters, the state transition, and the observations. Now the output is the action by the decision module, and we're going to have it executed by the robot, and then we get the observation from the sensors, and we connect them together, right? And it becomes a recurrent neural network, and if we unroll it, you can see that our state estimator and gets sent the state estimation, the probability distribution into the decision module, it computes the action, and so on and so forth, repeats over time, right? Now, we are going to use this architecture to perform partially observable visual navigation. So the input to the robot is an abstract map, a 2D floor plan, like an occupancy grid, and it uses a single monocular camera looking forward. And we are going to have to build an observation model in order to localize the robot. It is partially observable because the robot doesn't exactly know where it is in the environment. Okay. Now, we are going to train this robust this learning system using a bunch of imitation label data. So in total, 10K demonstrations, and we are going to test it on 500 different maps. Right? Now, think about that. Suppose we are going to solve this problem in our traditional model-based methods. Right? So one issue is that we have to build an observation likelihood model, which is what's the probability of a particular visual observation, like an image, given the current pose of the robot in the world and given its map. right? So we have to come up with a probably likelihood model for the space of images, and that is very difficult to build, right? Even if I manage to do that. But even if I manage to do that, and all sorts of assumptions I used in building this model may be very brittle and may be broken. And then when I put it into the real, and everything is going to break apart, right? Now, how about model-free deep learning? I think Davide earlier also mentioned that. Let's have this magic neural group, right? And then we can train. Yeah, you can train it if you get enough data, and you will be able to. You will succeed. Problem is that we have 10,000 different environments over there, right? So how do we get enough data to cover all of them? That's usually difficult. So now this is a comparison, right? So this is our differentiable algorithm network in the middle, and if you compare it with the model-free training, it really shows that by encoding the algorithm and the model and the structure into a neural network policy representation, it reduces the data requirements for training, and that's really the gap between the differentiable algorithm network and the model-free, the neural group. Okay? And then if you compare it with a pure model-based representation, the approach, this gap is there because we trained the neural network end-to-end using real-world data, right? So that make it robust and avoid overfitting to the assumption of the model. And now we also tried it for partially observable navigation without a map. Now, if we don't have a map, we have to add in an additional module, just like in any of the robot systems, that we can add in an additional module for mapping as well, right? So once we complete this thing, and then we can join the habitat, and for a few days, we actually rose to the very top of the leaderboard. I think that's 2 years ago. Okay, this is the, you can see that it's navigate in a complex visual environment while it's building the occupancy grid map at the same time. Right? It's all learned. All right, so let me show you another. So far I have used a fairly simple discrete state space models and the state transition models and observations. Right, so that's kind of simple. What if I have a more complex task like manipulate a deformable object like this rope over here? What I want to do over here is to push this soft rope through the gap over there between the obstacles. So there are two potential sources of sim to real gap. One is visual perception, and the other one is dynamics, right? So in our experimental setup, we use depth sensing. Therefore, the gap in perception is relatively small. So we're going to focus here on the difference in dynamics. We do not know the rigidity of the object in advance. Maybe that in the simulator, we assume that the object is very rigid. We actually trained a policy that's treating it as a rigid object. And then in the real world, then it's a softer rope. And can we succeed in this transfer, and how we are going to do it? Yeah, so the way we're going to do it is, first we are going to acquire an initial policy in the simulator. We assume that the object is actually rigid because it's simple. I mean, we can acquire this policy any way we like. We can do reinforcement learning, we can do demonstration, whatever we want to do. Get this initial policy, right? And then we are going to replan at every time step in the real world, and then based on the observations of execution, we are going to update the simulator parameters, the rigidity of the objects. Just to briefly recap, we have an initial policy, we replan every time step and executed the action. And based on the observation, we can update the simulator parameters. For in our particular case, that means the rigidity of the object. Right, to replan, given the current state, we consider K actions. The first action is taken from the initial policy that was trained in the simulator. And the other K-1 actions are just random actions for exploration. Right? Given after the first action, we just follow the initial policy. All right, so I'm just saying over here is that there's a judicial optimization for each of the traces over here. And then where does the simulator come in? And for every time we unroll the action, that we actually have to use the simulator as a predictive model of dynamics. And we use a differentiable simulator called DiffTaiChi. It's very recent. And now you can see that this entire structure over here now is differentiable, and therefore it's very easy that we can update the parameters of the theta. Now let's look at the result. Now we have the initial policy, which is trained in the simulator that assuming that the object is rigid. So now in the real, if the object is really rigid, we expect it to succeed. This is really the replay of the policy on a rigid object in the real. Now, if we change it to a soft object, that initial policy is kind of cannot get confused and doesn't know what to do. Now, after replanning, to close the gap in sim and real and updating the parameters, you can see that the robot actually gets a roll through this gap. To sum it up, what I'm proposing here is a differentiable algorithm network as a way to address a sim to real gap. The main idea here is to embed a model, in particular a simulation model, explicitly in a differentiable policy representation. And then we train the policy end to end from real world data. Right? Now, by using the algorithm and the model as a structure prior in the policy representation, we reduce the data requirements for learning and training with real world data and avoids overfitting to the simulator assumption, model assumptions. And that's all from me. And let me thank for the wonderful people that I work with. I'm Peter Kakis, is a student who is not finished. He worked on the differentiable algorithm network. He's now working at NVIDIA as a research scientist. And Sui Chen is working very hard on the defaultable objects now. Thank you.